So I'm going to be presenting the DLR hand arm system today. So this is a robot hand and arm system developed by the German Space Institute. And before we get started, I'll just like give everyone what this is. So just to go through what it looks like, it's some some pretty crazy looking biomimetic hand. And the whole thing is that they have variable stiffness actuators to provide compliance. And I'll go more into about what that means later. But we're just gonna have a quick overview of like what it actually is. So you can see it like hand ring stuff. So like a bit. The hammer and nail. That's the hand. And here's it like punching like very precise holes. I'm not sure if you can see it very well. And it's also able to actually drill stuff. Yeah, so back to the slides. This whole thing it's an anthropomorphic hand, which means that it's based off of the human biology. So the joints are trying to mimic what a human hand is actually a hand or system actually is. And then the important part is that it's variable of stiffness actuation, which means that each actuator is actually compliant. So like it has like some springiness. Like you can change how stiff the joint is. It's not like completely rigid like the like factory robots that you see. So factory robots, like it's very important that these guys are very, very accurate and they can replicate their motion like tens and millions of times, just because they're meant to do like a repeating task. So these robots have like very little compliance, like they just move. Slightly in the other direction, we have cobots. So this is like the ER5 arm, and these are compliant. So if like they're meant to work alongside humans, so they have to be safe. So if like a human bumps into it, it's not supposed to hurt the human or like it's not supposed to like swing wildly and like smack someone in the face. But how these are implemented is that they have like actual active, I guess like force feedback mechanisms. So this is something that needs to actually keep sampling on the force applied to it, and then it'll actually adjust the stiffness based on what it senses. So the problem with this is that you need to run like an actual sensing loop, and for very I guess fast things or very high burst actions, like for example catching a ball, your sample loop won't be fast enough to actually catch this, and then it's gonna look stiff when there's like a very rapid action. And on the very I guess right side, on the very other extreme, is that we have the human hand, and it's actually compliant adaptively. So if we were to catch a baseball, like our hands can actually like our arms can actually like tense up and get ready for this strike. So we can anticipate when an impact is going to happen, and we can adjust the stiffness of our arms to account for that. Another nice benefit of the human arm is that it's like elastic. So our tendons are able to absorb an impact and store that kinetic energy. So just this makes it much safer and like harder to damage these systems. Well, like if you imagine like this type of arm, right? Like if I were to like run a car into it, or maybe something like less extreme, like throw something big at it, because it's so stiff, it has a much higher chance of getting damaged. So kind of their whole observation was, if we're going to bring robots to the real world, like collisions are inevitable, so we should design around that idea and make things compliant. The next concept I'll have to go over is called antagonism. So in the human biology, since muscles actually aren't able to push, we need to have two, I guess, like actuators, if you will, for each degree of motion, or yeah, a degree, yeah, for each DOF. So for example, in the arm, we have a bicep and a tricep, and these will work together to move your arm. So the benefit of this is that we can activate both of these together to adjust the stiffness. So not only are we able to control this range of motion, but we can also variably adjust how stiff this is. So that was kind of what they took into consideration when creating this hand hardened system. Yeah, so this is just a high-level overview of what it's made out of. So for the upper arms, the four freedoms of the upper arm, they use something called a FSJ, which is a floating spring joint. And then they use something else down here for the forearm. So essentially, they broke the entire arm into two separate parts: the upper arm and the lower arm. And we'll go over more in detail for each of these. The arm is a pretty standard 3 doff shoulder plus a 1 doff elbow. The wrist has 2 degrees of freedom, and then the hand is 19. And this is slightly lower than the 27 in the actual human hand, but we'll go over like what type of changes they made for that. Okay, so to actually incorporate this variable spring actuation into the design, this is kind of the actuator that they came up with. So right here, this is your traditional, I guess, like brushless motor or whatever motor you have for that DOF. And then this is your gear reduction. So for traditional robotics, that's like only this left part is what there would be. And they kind of stuck this right part onto it. So they came up with a way to have this variable stiffness mechanism by using this motor, and it was able to adjust how stiff this part is. So if you drive it all the way up, it might just be like your standard robot, like a very stiff robot, or you can make it really elastic if you loosen this up, and then they attach it to the actual next link. So for the actual upper arm, this is like what the actuator actually looks like. So it's quite big, it's quite bulky, and here's a little cross section. This whole thing is quite complicated, and there's literally a separate paper on this. I initiated it in the chat on Discord if you're interested. But there's some like crazy engineering going on here. But essentially, all you can think of it as your standard robot actuator plus some type of mixed mechanism that is able to adjust how stiff it is. And before I move on, does anyone have like any questions?
Do you have any thoughts on like Clone?
I haven't looked too much into it, but I've just seen like their media. It's quite insane. I still, I'm not really sure all the things they've implemented, but it seems quite impressive.
Yeah, they until recently they had it was just their arm, but today I think I saw something where their abdominal, like their torso, it's also like has like muscles and fibers.
Yeah, it's
Know.
quite crazy. I remember I saw some of the early videos of the arm, and it's like really hella loud, but it looks quite great.
Mm-hmm.
Yeah, I also saw a video of it actually like walking around. Like I'm not sure if that was just a render or anything.
Oh, neat. Okay, no, I haven't seen that.
Yeah, but definitely very promising. Definitely keeping my eyes on them. 1 second. Yeah, what's up?
Wait, can you go back to the presentation?
Yeah.
What is a high? No, that's the next one. Yeah. What is like? What are the cam discs and the hypoid gear?
Yeah. Okay.
Have you looked into that?
Yeah. So I was looking at this. So this is the actual paper. They had like this 2D description of it, and to be honest, like I had very hard time like actually like visualizing what this is. So they had some like, description of it, but it's like very hard to see without like any type of render or like animation of it happening.
Yeah.
Yeah, I think to understand the actual like physical operation, so there's this another paper that actually goes like completely into this mechanism that I think we could look at. And I'll send the paper in the chat later. But yeah, I'm honestly not very sure of what's the heck's going on here.
Yeah, no, I saw this and I couldn't find any videos or anything. I'm like, I don't know how this works.
Yeah, this is basically all we have right here. Yeah,
all right.
they also have a patent for this actually. So I think the patent will probably go into much more detail over like what it actually is. But yeah.
Is there like a IRO robot that's actually using this arm design? Right now?
Yes. So this is like DLR's own robot is actually using this. So like if I go back to this, sorry, like this robot is using it. This is the robot they developed this arm for.
Oh yeah.
Yeah.
2016. Okay.
Yeah, or they worked on it like a long time ago. Like you feel like they started like 2008 or whatever.
Okay.
Yeah, it's called David, if you're interested.
Yo, your brother. Okay. Okay.
Yeah. Okay. So moving on, I'm gonna do a quick aside on this part right here. So as just a brief introduction, how traditional robot actuators are made is that they have some very high speed and like decently high torque. Maybe not super high torque motor here, so like a brushless motor, and this spins at like very high RPMs. But your robot arm doesn't need to move at like 1,000 RPM, right? It's not going to spin a lot, but you do want high torque. So essentially what people do a lot of the time is that they stick a gear reduction here, and what that would do is it would decrease the RPM and increase the torque. And there's a ton of different designs for this. So here are some animations of existing ones. A pretty common one is the planetary gearbox. So you have this sun disk in the middle, or sun gear in the middle, and you have these planet gears, and it's going to work together to reduce your, I guess, your RPM and increase your torque. So this one is quite easy to make, but it does have a couple of issues. So there's a bit of backlash. What that means is that as you drive the gear forward, it has a bit of wiggle room. So it can wiggle between like 1 degree and like 0 degrees and 1 degrees, for example. And that's just due to the context of the gears. Like they're not contacted perfectly. So they do have a bit of gives. And another issue is that they don't have very high reduction. So like, I think like you can only go up to like, I don't know, 10-1, for example, just due to the mechanical properties of this. So if you want to reduce your RPM or increase your torque by like more than that factor, you need to like stack these. And this gets like quite bulky over time. I mean, if you go to pretty high reductions. The next one is this like cyclodal drive, and this one's like actually super, super sick. Like I'm actually working on building one. Like I just got some CAD files online, and I was just working on making one myself to like see how it works. But essentially they use this like kind of like oscillating motion of this like this right here. So it actually like it's very hard to describe what it's doing, but if you just look at it, like it somehow works, and it does pretty well to reduce to fulfill the gear reduction. And the very cool part is that it actually has really low backlash. So the way that these gears are fit together makes it so it doesn't have very much give, and you can get to like pretty high reductions. So like as you increase the amount of teeth here, you get like 1 more factor of reduction. So you can go to like 100, like reduction of 100 to 1 like pretty easily. Yeah, so these are really cool. And then the third type, or not inclusive, but there's way more. But another type would be the harmonic drive. And they use like a flexible spline called a wave generator. And this can also go to very, very high reductions, and it's like incredibly precise. There's also like basically 0 backlash. So this is what you tend to see in a lot of humanoid robotics in like nowadays. And this is mostly used in the arms just because you want really, really precise control. But the problem is that like making this type of structure is like incredibly difficult, especially if you machine it and like use like strong materials. It's like incredibly expensive. And also it wears out pretty fast. So you do need to replace these much more often than these other ones. So this is like very, very great performance, but it's also like very, very high end. And I'll say it's mostly used in the arms. I think for cases where you actually just want a lot of torque or like a lot of power, you'll probably go with one of these too. Yeah, and that covers what happens in this section. Okay. Any questions on this? Questions or comments?
Could you go back to like maybe like 2 slides ago? I just want to look at that.
Yep.
Slide. One more slide back.
Yep.
This one. The arm, the wrist, and what are BAVs again?
I'll get to that. Yeah.
And antagonisms?
That's like this type of, oh, you can think of it as actuator pairs, but I'll explain more when we get to the BAV section.
Okay.
Yeah.
That's good. Okay.
Yeah. And then like basically we just looked at the floating spring joints. It makes up these 4 DOFs up here. Yeah. So okay. Let's move on to the more of the arm design. So they developed something called the bidirectional antagonistic variable stiffness joint, which is a huge mouthful. But essentially to realize this antagonism concept, so the ability, like we're having 2 actuators per degree of freedom, and the ability to vary its stiffness by driving both of them, or actually driving that degree of freedom by driving them in opposite directions. How they do that is they literally have 2 motors, and they pull and push or they pull in opposite directions. So you can imagine this as your bicep, and imagine this as your tricep. And then this will be your variable spring section here. So like it's literally all this is. It's like a pulley system, and you can pull this way or this way. So their observation was that when you pull in one direction, the other motor is like completely useless because this motor can't push the string or like whatever tendon forward, right? So you kind of have like really horrible weight to torque ratios. So at all times you have at least half of your motors like doing like literally nothing. And they're making it harder for the other motors to work because they're just adding their weight, like they're literally dead weight. So they developed this bidirectional antagonistic system where they use two pairs of tendons. So you actually use redundant tendons and they're like much lighter. But in this configuration, you can have each motor always be contributing its torque to the joint at all times. So imagine you're pulling it this way. This motor can also spin this direction and pull that same line in the same direction. So you essentially need half the torque on each motor to drive that link. Or another way to imagine is that you have double the torque for each link. So that's what this is. And yes, again, there is a separate paper on just this system. So there is a lot more to dive into here, but I'll just leave it for here. I'll just leave it here. And then moving on to the forearm design. So for the forearm part, they integrated the wrist movement and the hand movements all into this giant chunky forearm. So this is the 19-degree of freedom hand and the 2 degrees of freedom wrist. And if you recall, since we have this antagonistic design, we need 2 motors per degree of freedom, which means we actually have 42 servos in this arm. And then these are harmonic drive servos, and they're like quite small. So like you can already like kind of imagine how expensive this whole thing might be. And also there's like so much stuff going on right here, so much like mechanical motion, that it gets like really hot, and they actually need to like employ water cooling to keep this whole thing like at a reasonable temperature. So it's quite wild. But yeah, I'll dive into a bit more of how this thing is assembled together. So for the actual finger actuation, they use a servo to drive this kind of like pulley or a winder. So you can drive this finger by winding or unwinding this. And then like you can imagine like if you wind it, you can kind of pull your finger up. And if you unwind it, your finger kind of goes back down. And then to get the compliance, they have this kind of spring attached to these pulleys to get that kind of like springiness. And to get the exact desired finger behavior, so like your fingers will move differently like depending on which finger it is. So you have to like kind of adjust like the configuration or like the orientation of these pulleys and how like stiff the spring is, and then they'll get your exact finger behavior. And also it's really important that you have like a really good model of this hand just to take into consideration, just like to like take advantage of all of its compliance. So you need to do a lot of work to make this hand work basically. And then you can see this is how they kind of achieve the variable stiffness. Just by changing the orientation of this pulley right here, you can get like either a soft or a stiff setup. And for the actual wrist, so this part's quite interesting. Because they have all the servos in the forearm, you need to route all these tendons to the hand somehow, right? Like all these strings, they have to go to the hand, but your wrist also needs to move, right? So you don't want your tendons to all be disrupted when you move your wrist around. So they developed like quite a clever system. They call it the spherical anti-parallelogram configuration. And all this is doing is, first of all, is providing the 2 degrees of freedom in your wrist, and it's also making it really easy to route your wires through or your tendons through. They don't have too much visualization on what's going on, but these are just like steel bars, and these are like the areas on where your actuators will actually, I guess, like act on to drive the wrist. And this allows. Yep.
What do they mean by abduction? And adduction. Abduction
okay.
and adduction, yeah.
Okay, yeah. These are like more, I guess, like science terms. So abduction and adduction will be like kind of this motion in your wrist, like the side-to-side motion. This, and then flexion and extension will be kind of like your up and down motion in your wrist.
Okay.
Yeah, there's just like a lot of biology when you come into like biomimetic designs, so that's interesting too. Yeah, so kind of what they allow is 30 degrees. Wait, sorry, this is opposite actually. So it's 30 degrees. Like, sorry, this should be side to side. Yeah, that's why. Yeah, this is not up and down. This should be side to side. So it's 30 degrees side to side. I'm not sure what the exact range of motion for humans is, but this should be like quite similar. And the flexion and extension is 90 degrees, and it seems about right. So it's quite close to the human range of motion. So this seems quite complicated for just this 2-degree of freedom motion. But another benefit of this design is that it leaves like quite a lot of empty space in the middle for you to route your tendons through. And the exact like physical orientation of these joints makes it so that your palm and your forearm actually maintains like quite a similar distance apart. So there's also like less I guess stretching or like pulling on the tendons that actually goes through it. So that's like why this design is pretty cool. But once again, there's like not super much media on this, so like it's kind of just up to us to like kind of imagine what it looks like. Or if someone wants to like hack together like a 3D printed version, that'll also be pretty cool. But yeah, that's this forearm design. And just a quick comment, the real wrist actually has 6 degrees of freedom. And there's like, I don't know the exact number, but there's like 10 or 20 bones in your wrist that actually like interact in very, very complicated ways just to get this wrist motion. It's like your real wrist like isn't just you're up and down like this. There's also like actually some translation. So it's like very, very complicated, but they've just taken like they just basically said, okay, we don't need to mimic the arm or the wrist to the exactly the same as the humans, because those other 4 degrees of freedom like don't really matter. Because like they're very small, so you can approximate it with just these 2 degrees of freedom. Okay, and then for the actual hand, so the human hand is also like very complicated, of course. It's actually under actuated, which means that there are less, I guess, like actuators in the numbers of degrees of freedom. So you need like a lot of tendons in the hand actually work together to like accomplish all the degrees of freedom it has. In the actual hand, I believe it's like 27 degrees of freedom, but they've only implemented 19 here. So they've combined some degrees of freedom into like one actuated just to save on the number of servos. And just to make engineering easier, like just because they realized that like these degrees of freedom don't contribute that much significance to the dexterity of the hand, so might as well just omit them. So if you just look at this, these are like the actual degrees of freedom of each finger compared to the real ones. And then for the actual structure, for the finger base, they use something called a saddle joint. So you can kind of see that here, like these ones. Like they don't have very much media on this, so you kind of just have to like squint your eyes at them. And then the finger joints themselves are modeled as hinge joints. So these are just like your doors. And then you can see them here. So these are your hinge joints. And then your tendon will kind of go through it. And then as you wind and wind, these fingers will curl and like uncurl. Okay. So that was the mechanical side of it. And then to actually control the stuff in software, you need some pretty robust control algorithms. For the arm itself, if you just stuck with position control, it actually ends up oscillating a lot. So you really need to take into account all the, I guess, elasticity of the arm. So they use something called eigenmode decoupling. I honestly was not sure what this is. Like, I think we need to look at the paper more, but it was some pretty advanced control stuff. But it's essentially you require position-based control, but you also need to take into consideration the elasticity of those joints. And then for the finger control, there's a couple of other things you need to take into consideration. You need to make sure all those tendons are constantly pulled so you don't have any slack in them, because that can cause a lot of issues. Like your finger will just droop around, or they may get like tangled somewhere. It's also important that even though the spherical antiparallelogram system minimizes the amount of displacement of the wrist of the finger tendons, you still need to model like how the tendons get displaced as the wrist moves. Like if you imagine like you move your wrist like kind of like this, it's like inevitable that those tendons will get like kind of displaced. So you have to like model all that stuff too. So essentially, you just need to do a lot of modeling and really understand your system really well to be able to take advantage of all of its benefits. For the actual electronics, since there's like a ridiculous amount of servos and sensors, you need a very high bandwidth, and they use something called the BIS bus, which is bidirectional and also serial. So that's just like the technology they chose. And then they also transmit all that data to whatever compute you have. using something called SpaceWire, which is literally a communication protocol used in the space industry, which is kind of crazy. But it also makes sense because they're the German Space Institute. And then the third thing that you kind of need is a power supply that's able to supply a lot of power in a really short amount of time. Because imagine like you can go from your arm being completely at rest to like actuating almost every single degree of freedom like all at once. Like if you're catching a ball, you need to react very, very quickly. So they also developed like a custom power supply that's able to meet these requirements. And then yeah, so that's like the brief overview of the hand arm system. And kind of the takeaways I had from this is that in the real world, if you're going to deploy a robot to do things in the messy human world, it's going to collide with stuff. So you need to embrace that rather than try to avoid it. And then the way you do that is you have variable stiffness. And then the third kind of thing is you should learn from human anatomy, but don't copy it blindly. It's like don't try to mimic every single degree of freedom if you don't need to. You can approximate the behavior to get the results that you want. Yeah, so that was overview of this paper. So anyone has any questions?
Did they explain more? I didn't read much on the electronics part. Did they explain more on how they controlled all of those servos?
Like, do you want like what do you mean they control them?
Like, just you like elaborate a little bit more on the electronics part.
Like the actual physical electronics, or are you talking about the software control?
The software control.
Oh, okay. Yeah, it's quite a complicated system, and I don't think they elaborate too much on it. So I actually can't comment that much on exactly what they do. But yeah, I think you need to either look more to the papers or like the papers they referenced for that information.
Mm-hmm. Okay.
Yeah, it's like something specific you want to know. Maybe I can try my best to answer.
I just I saw the diagram that you posted. Yeah, I'm like, okay, I don't get this. So
yeah, there's a lot of stuff going on. But essentially there's something called impedance control where you kind of see impedance control is essentially you control how stiff something is. So you have a target stiffness and that you try to match that. So like if you want this joint to be kind of floppy, then you have like a lower impedance and you try to match that impedance. But if you want to be really stiff, then you have like a different target.
Yeah.
Yeah.
Okay. I'll listen to that.
Do you know how much this robot costs?
Let's see. I imagine quite a lot. I'm not sure if they actually disclose it, but like I thought each of those servos are already like a couple $100.
It's called Daniel, right?
David.
David.
Yeah. Yeah, I don't think I saw a price anywhere.
Also, did they do like any testing on it? Like, was there any like failure cases that it does really well on, anything like that? In the paper.
They don't go that much into I guess like experimental stuff in the paper. They just show it hammering something. That's about it.
I see.
Yeah. As for limitations, I don't think I actually saw very much in terms of limitations.
I see. Okay.
Yeah. But yeah, I could definitely link the like the subpapers and also the patent for more information.
Wait, so the new like the big like robots right now is like 1X and like the ones from Tesla. They don't use this method, right? I don't think so.
Yeah, so I believe a lot of the existing humanoids just do your kind of traditional I guess like motor with reduction method. 1X is interesting because they actually do use a tendon-driven system, but I don't think they've released too much information on like the exact details. Like we're not sure if it's variable stiffness or anything. But like the one really cool thing about 1X is that they kind of designed it from the ground up for operating in the home. So they really care about having the robot be safe and compliant, which is why they went for the tendon-driven approach.
Yeah. So is this okay, I'm a bit confused. Do you think this is only for like rotary actuators only, right? Or
Pardon?
this is only for rotary actuators, right?
Yeah.
Not linear. Because I remember the Tesla's one was they're using like linear actuators.
Mm. Yeah,
In their
this design only uses rotary ones. I think they basically only use servos.
mhm.
Or they only use servos in the forearm, but they do use like, I don't think they say exactly what they use, but they use some other type of DC motor in the upper arm.
Mhm.
Yeah. It's actually interesting. So a lot of the critiques of tendon-driven systems I hear is that they actually don't have very good torque.
Mhm.
There was another paper by Korea Tech where what they essentially did was that they moved all the, I guess, actuators to like as high up as possible, and then they had their, I guess, gear reduction or the pulley system lower down in the arm. So they have this kind of like torque amplification
Mhm.
lower down the arm, and they kind of just route all the tendons through. So that one was really interesting, and that they were able to increase the torque by quite a lot. And like I think they showed it catching a ball and stuff.
Oh, that's crazy.
Yeah.
Okay, yeah. Please link.
Yeah. But I don't think that DLR did any type of like pulley stuff to increase the torque like after it kind of like leaves the actual actuator.
Actually, okay. Yeah. Okay. I searched up a little bit on like impedance control, and I thought that was like the whole spring dampening system that they were using. So I thought they're using some kind of pulley system inside their arm
Yeah, they had like the
somewhere.
whole cam disk assembly. Like I really wish I could find some type of animation on like exactly how it worked. But it's like crazy complicated looking.
Yeah. I mean, I don't probably understand how normal these work. So this one's already a bit too much. Okay, I'll take it.
Yeah, but I think like kind of the cool lesson we got from this is like actually taking variable stiffness into account, rather than having these like super stiff robots with like active compliance control.
I wonder how you can like extend it, like with something that people found that spots. Yeah,
So what was
because
that?
you would assume you would assume that having stiffness would be better because it's like more stronger, I guess, and
Well, yeah, I
I
mean,
don't know.
but you can imagine like you have this like super stiff robot, like it won't move no matter what, right? And then like I don't know, like you like run into it, right? Like the human or
Yeah,
whatever that runs into it is gonna get hurt. Or if it's like the robot's like using all of its like torque to like maintain that exact position, it's also gonna damage itself. It's like you want
yeah,
to be able to absorb some of that impact, right? Like if your joints have that
yeah,
like the compliance, it can transfer that energy into its whatever energy storage mechanism, like the tendons, for example, and just avoid the
yeah.
damage from its actually important parts like the motors and stuff.
Yeah, I'm just like wondering what other like what other things that we do that like stores energy like that. Um, like I know jumping
Mm,
is also like some weird. There's like some pretty complex mechanism of like when you
yeah,
jump from like a high place.
right,
Um,
right.
uh, yeah, just wondering how we could like translate that concept
Yeah, life
maybe.
systems are interesting. Like I haven't looked too much into them, but I'm sure they're also like pretty interesting.
Mhm.
Yeah, I think to comment more on the hand, another common approach that you see is that rather than having this tendon-driven system, people also tend to just use microservos and embed them in the hand directly. So like rather than having like ropes that come through the wrist, they'll literally put the servos on each joint that they need to be. So this is obviously bottlenecked by how small you can make each of these servos. And it gets like really, really expensive, like once you get really small, because you need like some very precision manufacturing. And also, if they're so small, they don't really provide the torque that you need anymore. But like the most expensive hands, like I think like Shadow Hand is one of them. Like I believe that all of these just have the servos on the actual hand itself rather than using tandem systems. So that's like another approach to be aware of. Okay. Any other comments on what we read? Any thoughts? Any discussion questions? Okay, cool. I guess we could call it here today. Let me stop the recording.